Oh, we're starting. Okay, sounds good. No warning at all.
Okay, you didn't get a lunch ticket. Remember to get it from the front desk.
Yeah, because it was okay, so let's resume the lecture of Alvaro now.
Thank you. So maybe I just wanted to make a couple of comments that came up during the break before we move on to the next thing. First things first. Why is it called diffinvariance? So probably should have said that. So maybe this was like secretly in the definition. So let's take a particular case here. So I have a bundle that is natural. What this means that if I have a diffeomorphism of a manifold, right? That's an embedding in particular. This means that given this diffeo, it gets upgraded to an automorphism of the bundle. So what this is saying is that, well, my bundle basically admits an action by the diffeomorphisms of the base manifold, right? I'm lifting the action of diff M to the bundle itself. That's why we call it diffinvariance. Okay, that was a comment. Another comment was, what did I mean exactly by a natural operator? And you can think, I mean, what we've said is like natural bundles are basically functors, right? For every manifold, I get a bundle on top of it. And what we're saying is, what's a natural operator? Well, it's something that basically you take two bundles, E and F, both of them natural. Now I've said if I take jets, that's still natural. And now I want basically, well, a natural transformation, right? Something that maps, let's say, JRE to F, again, with such that it's invariant under diffeomorphisms. So the ramp is like that. So just think about that. That's one comment. Okay, final comment. Another question was like, can you give an example of something that is not diffinvariant? And in fact, Jasha already kind of spoiled all the cool, well, not all, but some cool examples. So let's see. So if I take isometric embeddings, what does this mean? I have two manifolds. I fixed Riemannian metrics, and I'm asking that, well, I can isometrically map one to the other. This is clearly not invariant under diffeomorphisms because as I apply a diffeomorphism, my source metric keeps moving, right? So this is not. And isocontact and isosymplectic embeddings have the same problem, right? You fixed a contact structure on both sides or a symplectic structure on both sides. Well, if I apply diffeomorphism that moves them, then this is not invariant. So these are like still pretty cool examples in the sense that this is like, you could call this that this is like isometry invariant, this is contactomorphism invariant, this is symplectomorphism invariant. But there's some things that are just terrible, right? If I just pick a random subset of jet space, there's like no chance it will be diffinvariant.
Maybe I want to add one thing.
Please.
So diffinvariance only refers to the source manifold and not to the target. For example, symplectic.
That's a very good read.
It's diffinvariant.
Yes.
Yes. So symplectic embedding. Yes. So,
Oh yeah. So maybe we should make the difference between isosymplectic. Yeah, maybe that's a very good comment. So I will maybe repeat this. So a very good comment of Kai is that we could maybe say, oh, what if I do just symplectic embeddings? And I should be careful what this means. I mean, this means in my target manifold, the symplectic structure is fixed. In my source manifold, nothing is fixed. But what I want is that the map pulls back the symplectic structure to a symplectic structure. Now in the target, there's nothing. So acting by diffeomorphisms is perfectly great. The problem appeared here when I also fixed a symplectic structure in the source, and I wanted that one to be the pullback of the other one. Very good. Thanks, Kai. Okay. Any other pressing questions? Okay, so let's see. So the plan for the second hour, the first hour was like basically language, like the necessary language we need to talk about each principle. The second hour is more like touching on some techniques that are quite important. One of them, for instance, is transversality, as Jasha alluded to. So I'm going to start with that. So let's do, I don't know what item this is, maybe. So what is the idea? The philosophy basically of transversality is that sometimes you want to construct, let's say, a solution of a partial differential relation, and it could happen that the complement of the relation is very small. So maybe let me write the idea first, and then we formalize it. So imagine I have a relation, and I take its complement, and this is very small. I will tell you what very small means. I mean, it just means it has, let's say, very high codimension. It says, let's say, some submanifold or a certified subspace that is super, super tiny. If this is the case, in some sense, you're saying kind of like the Taylor polynomials I like, they're like really most, right? The ones I don't like, they're like a super small part. So then you could imagine that this would imply that a generic, so let's say most sections should have, should satisfy that JRS avoids this complement. Right? It's so tiny that you could just avoid it, hopefully, by most sections, you would think. And if this is true, then this is precisely what it means that, well, if this is the case, then S is a solution. Yeah. Sometimes you can just build solutions because, in fact, most sections are solutions. And this is what we're going to implement. Maybe a comment. I mean, basically what I'm saying is in some situations you can just find solutions just by doing this. Sometimes doing this doesn't give you a solution. That's, for instance, what happened in Yasha's case when he was explaining inversions or embeddings. But still, transversality helps you to make kind of things reasonable by at least finding sections that don't interact too badly with this complement. That's still pretty cool. Maybe I will write that because maybe it's an important point to keep in mind. And I think that will be maybe some exercise for the later. Maybe even if not, so even if you cannot avoid, perhaps at least you have that this intersection is controlled. It's also small, let's say controlled. And that's good enough sometimes to do stuff. Okay. Okay, so maybe let me remind you what transversality is. If you, well, okay, maybe you've never seen it, and then here it is. So transversality is the following concept. So we're gonna say the following. So a map is transverse to some submanifold W at a point X if either one of the following things hold. Perhaps you just avoid this submanifold completely, or perhaps if you don't avoid it, at least kind of the F and W sit super nicely with respect to each other. This means the following: if I take the tangent space of M and I push it to N, then I want that together with the tangent space of W, they span the tangent space of N. So I mean, okay, this is best done by picture, to be honest. So let's say here's my W, and now here F shows up. Yeah. Maybe let me do what? This is F. And let's see, what do we have here? So for instance, a point, if we just avoid W, then that's just great. Okay, this is transverse. If we basically cross transversely W, this is what this says. It says I take the tangent space of the white thing, I take the tangent space of the red thing, and they span the whole tangent space of the manifold, then this is also transverse. This is transverse, this is transverse, this one is not transverse. Yeah, this is basically here that both tangent spaces are the same, so they don't span. So this point is not transverse. Thank you, Danny. Yeah. Why is this a natural thing to consider in this discussion? I mean, we'll see sometimes that the study of genericity is a study of transversality, even though a priori this seems like a concrete case. So the concrete statement I want to make here is that if I take a generic map and W is fixed, then a generic map will be transverse to W. Why is that true? Well, if you look here, what I could do is I can just push F a tiny bit. Right, so basically I could do a little push. Sorry. So here I could just take my F and I push it slightly, and now I get 2 points instead, and they are both transverse. So what this is saying, a generic map is intersecting W transversely. What is maybe less clear, but I will basically, I hope it does become clear, is that in some sense, all this genericity phenomena, they can all be phrased as this somehow. Okay, so let me tell you kind of the fundamental lemma that basically motivates doing this, or perhaps it tells you why this is a nice thing to consider. So the lemma says the following. If W has co-dimension equal to K, say, and M has dimension, as I mentioned nothing, this is kind of irrelevant, and F is transverse to W, then the preimage of W in M has co-dimension K. And here's a proof by picture, I suppose.
So did you already say it's a manifold?
It's a manifold. Yeah, I guess probably that's a good thing to say before I say it has a codimension. If it is as a manifold of codimension K. Thank you. Okay, so what is the deal? Here I have W, and at least locally, what saying codimension K basically means that you have a map. Let me draw this less dramatically. What you're saying basically is if a manifold, I mean, right, basically this is a manifold chart for W, but that basically says locally W is basically the preimage of 0 by some kind of regular function. So here maybe there's 0, and what we're saying this I call pi, and at least locally W is the regular preimage by pi of 0. Right? This basically says W is cut out by K linearly independent equations. Okay, so now if I have here M and I map F, the picture, right, is that, I mean, F is arriving like this. This is what transversality means. Right? This is really arriving like this, which means that this is kind of projecting nicely to our K. This means that, I mean, this was a submersion, right? This was a basically regular level set, but now the composition is also a regular, I mean, also has this 0 as a regular value. But here I have pi F, and what we're saying is that F minus 1 of W, is regular 0 level of pi preceded by. Right, what we're saying is W is cut out by K linearly independent equations. Then this composition, it's also K linearly independent equations that cut out this preimage. So here is. Okay. So this is very nice, right? Basically, it says, I mean, smooth functions or smooth sections or whatever, they're quite insane, right? They can behave extremely badly. But I mean, what you're saying basically is like, well, at least generically, hopefully, I mean, this is what we want to say, we will cut things very nicely so that basically K linearly independent equations also pull back to the same. Okay. So let me maybe give you the statement we want. I think I want to maybe write one corollary and then state tongue transversality. I will do yes, yes. A corollary that is quite important because it kind of ties to our goal there is that what you should observe is that if the codimension of W is greater than the dimension of M, what does this say? Well, this says and F is transverse to W, then what we just did, it says, well, the pre-image has codimension equal to the codimension of W, but I mean, it has codimension larger than the dimension, so it must be empty. Right? And this is basically our goal, right? It says if a thing is small, it can just be avoided. Okay, now without further
It
ado.
also follows from the concrete description, right?
Yes, agreed. Yeah, I mean, maybe I should say that. Indeed, right, if you just look at the definition, right, you say, I mean, being transverse is avoiding or spanning. And if the codimension is larger than the dimension, then these two things are not big enough to span. So you must get the other case. All right. And now let's get to the point. So now we're basically gonna explain that transversality is genericity. Something like this. So what is the setup? The setup is as follows. So given some sort of W, now inside of jet space, and you should think of this as sort of the complement of R. These are the things we want to avoid, but let's say so this is think. Then so what Tom proved is the following. You say, I take all the possible sections. I consider those whose RJet intersects this one transversely. And the claim is that among all sections, this is dense and open. And I should say W is closed. And I want here. Does it make sense?
Closed, you mean closed as in no boundary or closed as a subset? And
I want it closed as a subset.
Okay. Sorry, what are the assumptions?
So my assumptions are what? My assumptions is I fix a submanifold of jet space. This is closed as a
Does it
subset.
work for any manifold or
Yeah.
like?
No, this is absolutely general.
Okay.
I mean, in fact, this is not even the most general version. I mean, I could take here like more general. You can take a stratified subsets. So this would be something that is at least kind of it looks like a bunch of manifolds kind of assembled together. You can do also, for instance, like in line with what Jasha was doing of embeddings. There's some sort of multi-point version. So you could do something like instead of keeping track of a derivative at one point, I can keep track of derivatives at multiple points at once. So this would, for instance, be able to prove for you that I don't know, like for instance, like if you have like a knot projection, right? It has only double points, no triple points generically. Well, that's kind of some sort of transversality statement for multi-point conditions. So this is maybe, so let's say that this is kind of in some sense that almost the most basic version that you could state. Let's say. There's also something called the Tom Bormann theorem or certification, which kind of pumps this up kind of further in some other ways. So, okay, this is good enough for many things. Are there more questions?
you want to avoid
Say it again, say it again.
I thought you wanted to avoid
Right, but I haven't done it yet. Because I mean, what this theorem says is, well, if W is quite big, if the codimension is not big enough, then I'm just transverse, generically, I cannot avoid it. But that's where the corollary comes, right? The corollary says, well, if W is small, then I'm fine, then I do avoid. In fact, let me maybe write that as a corollary. I think that's in fact what I wanted to do. Yes, maybe let's do that. So corollary. Maybe let me phrase it in a way that connects to the H-principle language we've introduced. So if you have a differential relation you're interested in solving, and as complement of codimension. Let's see, what's the first case? So what we just said, according to that corollary, is if the codimension is bigger than the dimension of M itself, then I will be able to avoid, generically I'm transverse, and the corollary says then I'm generically disjoint. But then what does this imply? This implies that I can always find, most sections are solutions. So in particular, the space of solutions is non-empty. And you're saying something much stronger, right? You're saying most sections are in fact solutions. And now I want to maybe say a follow-up comment that maybe also explains a bit a slight generalization of this theorem. Suppose that in fact W is even smaller. It's even larger than the dimension of M plus 1. Then what you can try to do, basically, let me write the punchline. And then what does this say? What is going on here? So what I'm saying is, if W is even smaller, what I did here is I said most S's are solutions. What does this one say? This says, now I take paths of sections, and generically, right, I've gained one dimension, I'm considering a path of things now, but this is smaller, right? So then a path will avoid this W, which means that the whole path becomes a path of solutions at once. Which means that if the endpoints were already solutions, I've obtained a path that connects them, which means that the pi 0 is just, there's only one component. So what this is saying, kind of the overall punchline, is that the more, kind of quite naively, the larger the codimension of W, the more homotopy groups of the solutions you're able to say are trivial. So let me just leave that as keep going for higher families. And there's one example that maybe I want to mention concretely because I think maybe it's familiar to you. Maybe not on this board. I know. Can you move the camera? Yes. Very good. So the corollary that is quite typical, or like the concrete example to keep in mind, is the following. So suppose I have, let M be of dimension M and N of dimension N. Then the space, let me just write it. So these are the immersions. I could write this as the solutions of the immersion relation that I will discuss momentarily, maybe as an example. Is, let's see, what is this? 2n minus m connected. There may be a plus 1 somewhere. Am I writing this? N minus 1. Okay, whatever. Maybe there's a plus 1 or something. Maybe Sander can say. Oh, Sander isn't there. Okay, someone. Okay, there's maybe a plus 1. What is the point? What I'm saying is, the larger the target is, the easier it is to construct immersions. First immersion will certainly appear. The space of immersions will be non-empty when basically n is double the dimension of m.
I think this is not the space of immersions, but maybe the fiber.
Oh, I should take a fiber over formal. Yeah. No, wait. No. I want to say this, in fact.
But let's say M is the circle and N is the circle across a large Euclidean space. So the space of immersion.
Oh, right. Yeah, I should say. Oh, I shouldn't say formal, but I should say maps. Yeah. Okay. Let me just put that.
You can just.
Yeah, I don't want to. Because the correct thing to compare is not formal. Formal is also getting more similar to just normal maps. But maybe to avoid confusion, let me just write this. Thanks. You're totally correct. Yeah, I don't want topology maybe here. Yeah, so the point I wanted to make somehow is that the bigger the target is, the larger this W is becoming. So larger and larger families of maps are generically all immersions. Yeah. I mean, and for instance, this means that as n goes to infinity, then basically this is becoming contractible. Okay.
So for the corollary, we are assuming that R is nice enough that it has like the closed complement that it's
Yes. Yes, I mean, I mean, certainly when I'm saying this, I'm saying at least it's some stratified subset, and I can talk about dimension. And I always want things to be, the space of solutions to be open. So I want the complement to be closed. But okay, I'm gonna sweeping this under the rug, so to say.
It's a good exercise for the afternoon to show that the complement is stratified.
Yes, that's always, that's a fun one. So okay, that's a thing we will do for sure. Okay, so this was transversality. Are we sort of happy with this? I'm gonna kind of change gears and talk about handle decompositions briefly. Happy enough? Okay, so the next point is the following. So what we want to do, we want to basically implement the following idea. Let me maybe write it first. So I mean, I want to talk about handle decompositions. If you've done Morse theory, probably you've seen this before. I don't remember what this number is. And why are we doing this? So basically, an idea that is fruitful is the following. So something I said earlier, right, was the following. So what we start with, say, in a problem, is you start with some formal solution, right? So, and as we said, this is some sort of infinitesimal data. Infinitesimal. Right? This is basically at every point is still giving me a Taylor polynomial, and that Taylor polynomial solves my differential relation. Now, at the bottom of the board, what I want to put is I want to have an actual solution. Right? Somehow I want to pass from these infinitesimal things, I want to homotope them until I get an actual kind of global solution, little f. Okay, what's in the middle? What's in the middle is, well, the whole week, I guess. This is what the H principle is about, but I mean, you can imagine that there's some sort of patching argument, right? You pass from infinitesimal to some sort of local solutions, and those local solutions get deformed until you produce a global thing. So maybe you could imagine something like this. You could imagine that you get a bunch of solutions, let me call them SIs, that are actual solutions, but they are not defined in my whole manifold M. So maybe let me put M here now to indicate this. Maybe they are defined over some cover, kind of over some open, you have a little local solution. So this is, let's say this is local. And you have some sort of coherences between them. What does this say? This says, well, I have a bunch of local solutions, but I know they came from this like smoothly varying family of infinitesimal ones. So in the overlaps, I also know that I can still homotope them. This is what we're trying to work with. And where do handle decompositions come into this? Basically, what I'm trying to say is that maybe you can think that we're doing the following. We have something that is infinitesimal, right? It's at every individual point, a Taylor polynomial solving R is given. We've upgraded it to somehow like solutions that live in neighborhoods of points, plus some coherence between them, up to homotopy. And now here I want to pass to global. Well, there's something in the middle, you could imagine, right? I could basically try to patch up these things over subsets of M that are increasingly more complicated topologically. And what I'm kind of going with this is that maybe you can imagine that you're maybe working handle by handle, trying to patch up stuff. So that is kind of what is kind of in the middle here. Maybe you have kind of solutions over increasingly more complicated parts of M. And sometimes what is kind of interesting, I mean, I think this will be touched upon by Oleg, for instance, in the symplectic world, is that sometimes, in some sense, going from here to here, you don't even know how. So for some geometries, we know that if your manifold has handles up to dimension something, you're able to run the argument. But if it has handles of all dimensions, then you actually don't know how to prove a full each principle. So this is kind of really a kind of important thing. Somehow, like measuring the topological complexity of M in this way, it really is meaningful because for some geometries that's all you can do. You can only prove each principle up to certain size of handle. Okay, that was why maybe this is why I'm doing this. So now, well, if you know more theory, you can sleep. If not, I'm gonna tell you what handles are. So what is the idea? As I just said, I want to basically chop M into kind of simple pieces, so to speak. And the idea is the following. So given some W manifold with boundary, I want to say the following, attaching an I handle to W means the following. So maybe I will do the drawing and at the same time kind of write for you formally what I'm kind of explaining. So here is the boundary of W. And this is the interior. Maybe there's some topology. It's not important for what I'm going to do. And what we're going to do is basically we're going to attach, in some sense, attach a cell to W. So I'm going to attach this to produce a new manifold. And this is what's going to be an I handle. And what I have to explain to you as well is what this is and how I'm gluing. So what is the I handle? So the I handle is basically, it's just a ball, but I'm decomposing it into these two pieces. You should think basically, I mean, if you know what attaching cells to CW complexes is, this is the manifold version, right? If I want to attach an I cell to a manifold, we don't just attach the I if the manifold is not of dimension I. That's really reckless. What you have to do is stabilize it, right? You have to add some extra normal boundary. Okay, so we have this. And okay, I'm not gluing the whole thing. I'm kind of gluing kind of part of the boundary, which is this. So inside of here, you have basically the boundary of the first term. And where does this go? Well, this goes to the boundary of W. This is what I'm prescribing. This phi is what we call the attaching map. And now this lives in M, right? And basically what we're doing is basically we're putting these two things together along this map. Yeah. Maybe let me write it in the next board. But then we define a new space that is basically my M union the handle. And I'm attaching it along this kind of attaching area. Along this line. Yeah. So maybe let's draw things. So this part is this part. As I said, this is kind of some analogy. I mean, you should think of this as a thickened cell. So okay, here is the cell. Right. So this is the I. And maybe I can call this the core of the handle. Then there's its boundary, right? So this is a sphere, and we call this the attaching sphere. And this is probably all I want to say, I guess. Yeah. So why is this relevant? Oh, this is we have to stop in how much? At o'clock, no, or so, or a bit over.
No, you started a quarter past.
Oh, nice.
Alvaro,
Yes.
one question for these
Please.
differential relations. You say that there are examples where you can make it work up to some.
Yeah, let's go on. Yes.
No, so what example? I can go
No, okay. Maybe I should be careful because I mean I should maybe be precise. So for instance, let's say I take symplectic. So something Yash already said is right. Well, if you there's this theorem of Gromov that I think Danny will prove, that basically says on open manifolds, right? Then you have full H principle. So you would say, okay, this is some sort of H principle that goes up the way all the two handles, except kind of some sort of the maximal handle that closes the manifold. You could imagine that. Then again, I mean, there's some sort of other. I mean, that's kind of like one example. Maybe we're like kind of closing at the very end. You don't know how to do. But maybe even still in the symplectic case, you could say, well, what if I want not just to construct a symplectic structure, but some sort of symplectic structure that it's kind of like nicely adapted to the handle, the boundary of the handles is a reasonable object. Then this is maybe this Weinstein H principle, and that only runs up to like handles of dimension half. So sort of, yeah. There's maybe different flavors of this, but that's a bit of philosophy. And also, yeah, positive scalar curvature also work like this. Complex things, Stein things. Okay, so yes. So I mean, there's a theory. I mean, okay, maybe a comment about this. Maybe a little warning. It's not very important. I'm just gonna do a drawing. What I've just produced, this is not smooth. I mean, it's not a manifold with boundary. And why is that? It's because it has like a wacky corner, right? It's not even a very normal corner. It's like a 3/4 kind of corner. So that's not very good. We want manifolds with boundary to somehow run this like reasonably, but you can always do the following picture. I'm gonna do it now with the same colors for consistency. So we have this. We have our handle is arriving to this area. Here it is. Ta, 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 ta. Okay, this is not smooth because these are not boundary points, they're corner points. But you can always do the following picture. Let me just maybe draw it directly. You can just do this, right? You can, there's basically some kind of model you can put that smooths out the corner. And the space of such a smoothing is contractible, blah, blah. Yeah. Basically, there's something that smooths it out for you. So this is a smooth out the corner. So now out of a manifold with boundary, we produce another manifold with boundary that has, well, it's like different topology. It has an I cell additional. And why this is important, I mean, this is maybe in some sense the main result of, I guess, Moore's theory. Is that this decomposition, you can always produce it. So let me see, I mean, do I want to, yeah, maybe I want to state it maybe for compact because I want to make some points that are for compact, but okay. So let M be compact and possibly with boundary. Then it has a handle decomposition. This is very much non-unique. So now understanding maybe how unique it is kind of interesting thing. So this is kind of important, right? Basically, this says this recipe makes sense, right? Because, well, every manifold can be decomposed like this, and now it makes sense to try to do what we did here, which is try to work handle by handle at a time. And moreover, there's some kind of extra stuff you can achieve that I think maybe will be relevant in some course, maybe Oleg's. So handles attach with increasing I is this number I put there. I called it the I handle, and this has a name. This is called the index of the handle. And moreover, you can basically normalize the smallest and the top handle. So if M connected, then you can achieve that there's a unique zero handle and top handle. I think these are the things I wanted to say. Oh yeah, I wanted to say maybe one more thing, sorry. So maybe I should say it like this. So at most, Okay, I'm not gonna write here. This is more important. Maybe I will write it here because I'm gonna use it right now. And I think with this we'll finish. So the last property I also wanted is that we use at most one dimension M handle. And this is if and only if the boundary of M is empty. If there's boundary, you don't need a top handle. Okay. And now let's do things with this. Okay. So let me maybe explain this. I mean, where am I going with this? Where I'm going with this is that I want to maybe now combine this with transversality to try to make the point that, again, you'll see it also for each principles more in general, that if M is very simple topologically, then constructing solutions of things is easier. Okay. So let's do that. So to measure the complexity, I mean, now it's kind of clear maybe what I want to do. I want to say, well, a manifold is kind of simple if it's built out of little handles. So I'm going to define M as handle dimension J if it can be built with with handles of the index at most J. Yep. And what is like a key property is the following, and this is maybe best shown by picture. Please.
For this definition, do you include the top dimensional handle or not?
Say it again.
Do you include the top dimensional handle?
Yeah, I mean, so for instance, if the dimension is the handle dimension, then it means that I have to put handles all the way up, which means that I've closed my manifold.
In the index?
Right. So I mean, no. What?
So
But
if you
what-
have handles of dimension 1, 2, 3, 4, and then you jump to the top dimensional 8 or something.
Yeah, that's fine.
So that is all.
Yeah, that also counts, right? I mean, if I have some, let's say if I have a sphere, right? I mean, I can do a handle thing where like there's a zero handle and there's only the top handle, and then the handle dimension will be the dimension.
For every closed manifold, its handle dimension equals its dimension.
Yes. Okay. Maybe let's write that for sanity's check. If the boundary of M is empty, then the dimension of M is the handle dimension.
And then it's compact.
Yeah, sorry. If compact. Thank you. Okay. Where are we going with this? Yes. So what is the point? So a lemma that basically I suppose you can believe from the way we introduced it is the following. So if M has handle dimension J, then there exists a k-dimensional skeleton. And what does this mean? This means the following. It means that there's a CW complex inside of W, and M is inside of M, and M is homotope equivalent to this CW complex. How do you build it? Well, I mean, I just said, right, that if you have handle dimension J, that means that you're building your manifold using cells of dimension at most J. So if you put all those cells together, that's exactly what the skeleton is.
J dimension?
Yeah, so let me write. Oh, I'm not consistent with my letters. Sorry. Thank you. So this is basically, this is a CW complex of dimension. Well, okay, this I already say J-dimensional, such that M, let's say the formation retracts to it. in some sort of a smooth way.
Skeletons roughly cores of the handles.
Yes. Maybe that will be the proof. The proof, open quotes, is that K is basically the union of all the cores of handles. But I have to be slightly careful about how I phrase this. I mean, in the picture that I did, my core is running up to here, but somehow you have to continue it in a sensible way down to the existing skeleton. But okay, let me not elaborate on that. I just want to make a final point with transversality, some sort of application, and then I think that will be a good stopping point. So what is the point? The claim is the following. Maybe this is some sort of corollary or of non-transversality. So it says the following. So the idea is that, as I said, if M is very simple topologically, meaning that it has a very small handle dimension, H principle should become easier, you would say. And the precise statement is this. So do I still have transversality? No. So suppose again that we have some W. Once again, you should think that this is something we want to avoid. So maybe this is the complement of our relation. Closed, say, and of dimension equal to K. Suppose, moreover, R is diff invariant. And you'll see in the proof why this pops up. Then you can do the following. Then, let me write it like this. If K is larger than the handle dimension of M, then we have some solution. Does it make sense? So I'm saying if we have some relation and its complement is small enough, it's small enough in the sense that basically the core, right, the skeleton of the manifold should avoid it generically, then that's in fact true. And let me run the proof, and hopefully you will see how diff invariance enters and how the size enters, and then that will be a good stopping point, I think. So the proof is the following. So the key point, right, is exactly this inequality. It says, well, I mean, the handle is so small that it should avoid W. So that's actually what Tom tells you. Tom says a generic section of E has that satisfies that JRS applied to the skeleton is disjoint from W. Okay, what does this mean? I mean, if we are avoiding W, I mean, if I'm avoiding, since this is closed, and the skeleton is also closed, I can take a little neighborhood that still avoids. So this implies, okay, there is some neighborhood. Let's call it U. Okay, such that JRS of U also doesn't see W. And now I'm going to use the skeleton property. The skeleton property basically says, I mean, I phrased that kind of sloppily, but what it says is basically there's some neighborhood of K that is isotopic to M. It's kind of basically a thickening K produces M as a manifold. So this is one property. The other property is that U and M are isotopic. Okay, but then this is pretty great because we're saying, okay, I'm avoiding this W. This implies that at least, I mean, S is not a global solution because I'm not avoiding W everywhere, but at least I'm avoiding it over U. Right, so this means that S restricted to U indeed is a solution, but in U. Yeah. But now this is why diff invariance enters, right? Diff invariance says, well, I mean, U and M are actually different, like the same manifold. And I have found a solution on U. So by naturality, I can pull it back to the whole. So now diff invariance of R. Let me give this a name. So maybe the isotropy here is called phi. This implies that I can pull back S to the whole of M. So now this is a section of the whole over the whole thing. And in fact, well, in fact, it's a solution. Yep. And I want to maybe make a comment that I think is maybe important to keep in mind. So what have we done? So we basically said, I mean, very earlier when we applied some transversality, we said, if you have enough codimension, then a generic section will be a solution. Okay. What is this? Is that also true here? No. One second. Then let me finish this. So this says a generic section over U is a solution, but away it's not, right? I mean, what I have to do to globalize is I have to do this pulling back to the whole manifold. And this kind of breaks this like generic section, right? I mean, this isotropy that pulls from U to the big thing is changing S ridiculously much. And you're basically all the rubbish, all the stuff that was like basically in the complement of U, all the stuff that was possibly saying W is getting pulled out to infinity. And that's kind of maybe a quite important idea in principle somehow, that what you do is you do this kind of local solving in a skeleton, and then the rubbish gets pushed away. Pushing to infinity is a good thing. Okay, I think this is maybe a good stopping point, and then we can do questions. Yeah.